All right, so in this last video, or in the last video, we talked about the magnetic force on a current carrying wire because it is in a magnetic field. It's a cross product equation, meaning that the current in the wire must be flowing perpendicularly to the magnetic field that the wire is in. The magnitude of this force depends upon how much current is flowing, the length of the wire in the magnetic field, the strength of the magnetic field the wire is in, and then sine of phi, where phi is specifically the angle between L and B. Well, if I have two wires, I have an I1 and an I2. I'm going to just say I2, they're both carrying current upwards at the moment. Well, I know both wires individually will be creating a magnetic field. So for example, wire 1 creates a magnetic field that loops around it. From the right-hand rule, if I put my thumb in the direction of this current, oh, sorry, that doesn't say thumb, does it? Thumb in the direction of this current, my fingertips are my arrows that represent which way around this wire the magnetic field will circle. So the magnetic field due to wire 1, I'll call it B1, goes in on the right side and comes out on the left side. The strength of this field, we can use B of a wire, is mu naught times the current divided by 2 pi d. D is however far from this wire that I'm trying to find the field. So where I drew these X's and dots originally, D would just be from the wire to the dot. But this magnetic field, there's concentric rings that represent the magnetic field around this wire. The field gets weaker the farther away from the wire, but there is a magnetic field. Ultimately, what that means to us is that over here, in this region of space where wire 2 happens to be located, there is a magnetic field created by wire 1 that points into the screen. It would come out on the other side, out of the screen. The strength of this field depends upon how much current is flowing in wire 1 and the distance, D, specifically between the wires. Because I want to know the strength of the field where wire 2 exists. So that means I'm a distance D away from wire 1, which ultimately means the distance between the wires. So in terms of the magnitude, the force on wire 2, so magnetic force on wire 2 due to wire 1. The magnitude, just using this equation on the left, it depends upon the current flowing through wire 2. It depends upon the length of wire 2 in this region. So the length of the wires that are the same. And then it depends upon the strength of the magnetic field created by wire 1. If wire 1 wasn't there, there wouldn't be a magnetic field, and then there would not be a magnetic force on wire 2. So it's because wire 1 is creating a magnetic field there, and because I2, there is current flowing through this right-hand wire, that's why we have a magnetic force on wire 2. Now, phi is the angle between the direction of current flow in wire 2. So the current flow, I2 is up. We use that to define the direction of L. The magnetic field is into the screen. So B1 is into the screen. The angle between these two vectors is 90 degrees. So we can simplify this in this case. F2 will be the current I2 flowing through that right-hand wire, the length of the wire, and B1. But we know B1, the strength of the magnetic field there is I1 over, well, mu naught I1 over 2 pi d. So the magnitude of the force that wire 2 is experiencing because it is in a magnetic field that wire 1 is creating, mu naught is still there. We actually have both I1 and I2 in here, and then L over 2 pi d. So this would be the strength, the magnitude of the force created or exerted on wire 2 because of wire 1. And it's also because they're both carrying current. It turns out that if we went through the same process for wire 1 would be creating its own magnetic field as well that comes out on the left side, goes in on the right side. So wire 2 would be creating a magnetic field over here that would depend upon the current flowing through wire 2 and how far away from wire 2. The force on wire 1, using the same equation up here, depends upon the current flowing through it, the length of the wire, and the strength of the magnetic field over where wire 1 is due to wire 2. But if we go plug in these numbers in, this equation ends up being the exact same equation that we just got for wire 2. Which hopefully makes sense. If you remember Newton's third law, the force on wire 2, because of wire 1, needs to also be the force on wire 1 because of wire 2. So what one object, the force that exerts on a second object, the second object exerts the same but opposite direction force back on the first object. Okay, let's talk about the direction of the force. To do that, we need to use the right-hand rule. If we do this for wire 2, so for F2 specifically, okay, our thumb always goes in the direction of the first vector in the cross product. Well, the first vector here is technically L, but the direction is determined by the direction of I. So in my picture, I drew I2 pointing up towards the top of the screen. So we need to take our right hand and point our thumb in the direction that represents towards the top of the screen. Our index or pointer finger needs to point in the direction of the magnetic field. Well, wire 2 is experiencing a force because of the magnetic field wire 1 is creating. And we already determined that. If we come back up to our picture, we said B1 at that location would point into the screen. So if I have my thumb pointing in the direction that represents the top of the screen, my index finger pointing into the screen, my middle finger, in this specific case, will point to the left. What that means is wire 2 experiences a force that points to the left. So if I come up to wire 2, I can draw a vector pointing to the left that represents this magnetic force that wire 2 experiences. So wire 2 is attracted to wire 1. Well, Newton's third law, not only do these forces have to have the same magnitude, they also have to have the same direction, opposite directions. For every action, there's an equal and opposite reaction. So if wire 2 is attracted to wire 1, then wire 1 is attracted to wire 2. Now, conveniently, in the test notes, if you read the paragraph right above these equations, well, the equation, it's not written twice. The paragraph above that equation tells us that parallel wires with current moving in the same direction, like I just drew. So if the current is moving in the same direction, they attract each other, which is what we just saw. Using the right-hand rule, we came up with it. But because this is written out in the paragraph right above the equation, we can just use that. We don't have to do the right-hand rule again, though we can. If the current is in the same direction, they're going to attract. The wires will attract. If I is in the opposite, then they repel. Meaning, if my current flowing up was I1, but I2, instead its current was flowing down, then these wires would experience forces away from the other wire. The magnitude would still be calculated using the same equation, but the direction would just be opposite.